Okay, I think we can begin now. So, hello everyone, this is Tanya. I'm one of the TAs assigned to the course Aircraft Design taught by Professor A.K. Ghosh. So, we will go over the contents of week 3 and week 4, discuss the assignments of week 3. Okay. Before we begin, we'll just discuss the basic nomenclature of an airfoil. I'm sure all of you already know this, but we'll just go over it once so that all the other questions are easy to solve and no terms are new and you're familiar with the terms. Okay, so an airfoil has a leading edge and a trailing edge. So, yeah, this is the leading edge and this is the trailing edge. Well, this line in orange is called the chord line. What is the chord line?
A straight line joining the leading edge and the trailing edge.
Absolutely right. So that is a straight line joining the leading edge and the trailing edge. Then you have this line in green called the mean camber line. What is the mean camber line?
It is the equidistant line from upper and lower surface.
Again, right. So these are the two basic lines that we will discuss throughout the course. Chord line is used to define the angle of attack. The camber line gives you an amount of how much there is curvature in the cross section of the wing. Okay. And the other terms with which we characterize airfoils are maximum thickness, the maximum camber, and the leading edge radius. So leading edge is in the form of the leading edge, that portion is in the form of arc of a circle. So the radius of that arc is denoted by this blue line here. Then you have the maximum thickness. Maximum thickness and maximum camber are different. They need not be the same point. The maximum camber is the maximum distance that the mean camber line has from the chord line. And the maximum thickness is the maximum distance between the upper surface and the lower surface. They can be the same point, but they need not be the same point. Okay. And all of the locations of these points, that is maximum thickness point, maximum camber point, trailing edge, all of them are measured with respect to some reference. In our case, in the case of airfoil, we will take the convention of leading edge. So all distances are measured along the chord line from the leading edge. So you can see this location of maximum camber, location of maximum thickness, the trailing edge, the chord line itself, they're all measured from the leading edge. So your reference point here is the leading edge. Okay, so yeah, this is a slide from previous session as well. So we'll just go over it. What are the points of an airfoil that help us to design or choose the airfoil for our required mission? So the aerodynamic characteristics are CL alpha, alpha stall, CL max, critical Mach number, CMAC, that is the pitching moment about the aerodynamic center of the wing of the airfoil. And then you have some geometric parameters, that is the nose radius, thickness to chord ratio, maximum camber, all of those, right? So maximum camber, location of maximum camber, location of minimum pressure. All of those are geometric parameters. These are your aerodynamic parameters. And these are geometric. Okay. So your CL alpha, like we discussed in the previous two sessions, we need a CL alpha to be as large as possible with change in angle of attack. So the curve, the lift curve slope, CL versus alpha, the slope is what is given by CL alpha, and we prefer it to be as steep as possible. So for a small change in alpha, you get a larger coefficient of lift. Another term here is ratio. Okay. So alpha stall, again, that we discussed in the previous two sessions, is the angle at which the aircraft will stall. So the angle at which the aircraft does not produce enough lift to sustain its weight. This happens due to flow separation on the upper surface of the airfoil, flow separation over the airfoil, and so it does not produce the necessary pressure difference, does not produce the necessary forces. And so we have a stall, that is, it does not produce sufficient lift. So we need to delay this. So we need to have as large a stalling angle as possible. Right? So if your stalling angle is 5, you can only fly in that range up to 5. If you have it at a larger angle, you can fly for a larger range. So what do you think will contribute towards increasing the stall angle? It has to be a geometrical parameter. Which one do you think will contribute towards increasing alpha stall?
T by C.
P by C, it does not directly affect. What parameter directly affects is the aspect ratio. think this was discussed in the week 4 lectures by sir. So what happens is this CL versus alpha curve. So this is for suppose aspect ratio 5. And as the aspect ratio reduces, this slope becomes lesser. What happens is that the alpha stall at this point keeps moving away, keeps increasing. So this is for lower aspect ratio 1 or something. So aspect ratio directly affects the delay or the increasing of the alpha stall. So it allows you to fly for a larger range. Okay. So alpha stall is a parameter that directly influences alpha stall. Aspect ratio is the parameter that directly influences alpha stall. Next, we have CL max. CL max depends on a variety of parameters. One parameter that sir discussed in class was thickness to chord ratio, the graph of which is CL versus T by C is like this. So about 14 to 15% is where you get maximum CL. So that is the thickness to chord ratio that we pick to assign to our airfoil. Okay. Then we have critical Mach number. Critical Mach number is the free stream Mach number for which at some point on the airfoil, the airfoil witnesses a sonic number. So it witnesses Mach 1. So if your airfoil is something like this, and you have a M infinity, and at some point here you have Mach 1. So the flow accelerates above the airfoil, right? So if this point witnesses M infinity, the flow accelerates above the airfoil. Why does it accelerate above the airfoil? So if your M infinity here is suppose say 0.8, and your M infinity here in this case would be M critical, if I'm just taking a case, if this is the M critical, we know that at some point on the airfoil, it becomes Mach 1. That means some point on the airfoil, the Mach number, the velocity is higher than the leading edge. Why does the flow accelerate to a higher velocity?
Because of the shape of the aerofoil.
Yes, so because of the shape of the airfoil, what do you have? You have a change in the pressure distribution. So the pressure is reduced here, right? So when the pressure reduces, the speed increases, right?
Yes, ma'am.
Yes. So that is the reason. You're right. Shape of the airfoil is the reason why pressure reduces. So that is why you have a flow accelerating above the airfoil. So that is why the free stream Mach number can be less than Mach 1, but at some point on the airfoil, if it reaches Mach 1, this free stream Mach number is called critical Mach number. Again, like alpha stall, we need this number to be as high as possible because it will allow us to fly for a larger range of velocity. Okay. What parameter, this was discussed extensively in sir's lectures. What parameter affects critical Mach number?
Sweep back.
Sorry, I didn't hear you.
Sweep back.
Sweep back, and the ones that are sweep back is another geometric parameter. Sweep angle, okay. Yes. Another parameter here is thickness to chord ratio, correct?
Yes, ma'am. Thin aerofoil.
So you have a graph that goes like this. And this is T by C. And this is M critical. So M critical, he's right. It varies with respect to sweep angle for a wing. And for if it's an airfoil, like he said, it's thickness to chord ratio. Then you have CMAC. CMAC for a symmetric airfoil is 0. What about for a cambered airfoil? CMAC is the pitching moment coefficient about the aerodynamic center of the airfoil. Okay, so for a cambered airfoil, what will be the value?
Positive.
Positive. A cambered airfoil value will be negative, right?
Yes, ma'am. It will be next.
So if I take this as the airfoil, if this is your aerodynamic center, okay, let me just draw another. Okay. So when there is this pressure difference, it happens across a point called center of pressure. So that is where all of your forces are actually acting, lift, drag. Okay, so this is CP. But since this CP point varies with flight, so when the angle of attack increases, this CP varies. And it is difficult for us to perform analysis about this point. So we have taken a point called aerodynamic center, which remains constant with angle of attack. So it makes our analysis easier. So what we do is we shift these forces to this point. What happens when we shift the forces to aerodynamic center? It comes with a moment. So in this case, you have a negative moment for a cambered airfoil. For a symmetric airfoil, the CP and AC are at the same point. So your CMAC is 0. For a cambered airfoil, your AC is ahead of the CP. So when we transfer the forces to AC, you have a negative moment happening at negative moment that occurs at the AC. So we prefer not to have a negative CMAC, which is why we introduced an airfoil called reflex airfoil. What is a reflex airfoil? You have a slight upward bend towards the end. This will reduce the amount of lift generated, but it will ensure that your CMAC is positive or at least 0. Might not be 0, but it will not be negative because we prefer it to be positive because we don't want any unbalancing and destabilizing forces over there. Okay. So we'll just go over to the next slide. So this is a figure that Sir had discussed in class. This is with respect to the critical Mach number and drag divergence Mach number. So when the flow is less than the critical Mach number, less than 1, it flows smoothly over the surface. When it is at the critical Mach number, there is a point on the airfoil where we have sonic velocity, right? So there is one point where Mach number equal to 1. And anything above that, anything above the critical Mach number, over the airfoil, you will have a normal shock wave generated. When the normal shock wave is generated, you have a disturbance in the forces, the shock wave, boundary layer interaction, all of those destabilizing forces occur. You have more drag because of these interactions, and this is not favorable for us, which is why we had mentioned earlier that the critical Mach number should be as high as possible to allow us to operate for a long range. And aft of this shock wave, you have a possible flow separation. Now, what happens when you fly higher than this? So if this is even more high, I think I have a slide somewhere in this. We'll get to that later. But if it flies higher than this shock wave travels after, and there is a definite flow separation, which is not favorable, does not produce the necessary lift, and also comes with a lot of drag. Okay, so we need to increase our critical Mach number as far as possible. Now we'll just go over the NACA airfoil series. We'll just discuss the 4-digit, 5-digit, and 6-digit airfoil series. So we'll discuss it with an example so it is easy for us to follow. So 4-digit airfoil series, we take this 2412. Now in the 4-digit airfoil series, the first digit represents the value of maximum camber in 1/100th of C. So what will be the value here? Value of maximum camber will be 2 by 100 C. It will be 0.02 C. Correct. Now the second digit represents the location of this maximum camber in 1/10th of C. In our case, what will it be?
0.4 C.
Yes, exactly. So it will be 0.4 C. Similarly, the last two digits represent the maximum thickness in 1/100th of C. So here it will be
0.12 C.
Exactly. So the next slide just gives you these values. Now for a 5-digit series, the first digit when multiplied by 1.5 gives you the design lift coefficient in 1/10th of C. CL design. Okay. When multiplied with 1.5. So in our case, what will it be? It will be 2 into 1.5 by
0.3.
0.3.
Then the second and third digits, when divided by 2, gives you the location of maximum camber in 1/100th of C. Here, what will it be?
0.15.
Exactly. So 30 by 2 into 100 C, it will be 0.15 C. And the fourth and fifth digits, like the previous case, gives you the maximum thickness.
0.12.
Exactly. 0.12.
Ma'am,
Yes.
the first digit, ma'am, the design lift coefficient in terms of C, like in terms of chord, ma'am.
Oh, yes, that is a mistake. Thank you for pointing it out. It's not 1/10th of C, it's just 1/10. So it will not
Yes.
be C, it will just be 1/10. Correct. That is right. So I hope everybody's realized that.
So, ma'am, I need to know that this is the value of CL naught. Means when alpha is 0, then this is the designed value of CL.
Yes. Yes. Correct.
Okay.
For that airfoil, at what CL we designed it to fly. CL naught. Correct.
Okay.
So these are the values. Again, I think this error is there throughout. I'll change it when I upload it. So the C is not there. the lift coefficient is not in terms of C, it's just an absolute value. Okay. Yeah. Next, we have the 6-digit airfoil series. So here the first digit just represents a series number. So in this case, it's just 6. The second digit represents the location of minimum pressure in 1/10 of C. Okay. So that will be 5 C. Yes.
I think someone's mic is on and it is disturbing.
Soumya? Yeah, I think they've muted it. So the subscript here, this value represents the region or the range above and below the design lift coefficient where it is favorable. Favorable as in we have low drag. So the region above and below this design lift coefficient for which we have low drag. That is what is represented by this subscript. So in this case, it will be 0.1, right? The region or the range. So it's 0.1 above and 0.1 below the design lift coefficient. Then the design lift coefficient is represented by the third digit. Third digit here is this. The subscript is not considered as a digit. It's a subscript. So the third digit here gives you the design lift coefficient in 1/10. That is
0.2.
0.2. Exactly. The fourth and fifth digits again give you the maximum thickness in 1/10 of C. Again, it is 0.18 C. Okay. So those are just the values. Next, we have something known as supercritical airfoil. Again, this is discussed in the lectures. The advantages I've just summed up here is that it increases the drag divergence Mach number. What is the benefit of increasing the drag divergence? What is the drag divergence Mach number?
It is the Mach number at which the value of drag increases exponentially.
Yes, so the slope is really high, right? Yeah.
Yes, ma'am.
That is the value. So if we have a supercritical airfoil, we have a higher drag divergence Mach number. So what happens is that we can fly for a larger period without the drag increasing exponentially, like he said. So the range of operation with favorable conditions is larger. So supercritical airfoil helps us in that regard. Next, since we delay the flow, the shock waves and all of them are formed after. So if your conventional airfoil had shock wave forming here, for a supercritical airfoil, it will be delayed. How is a supercritical airfoil geometrically defined? It has a flatter upper surface. It will be something like this, and then you have the camber happening. Right? Towards the trailing edge, you have the camber, where the upper edge near the leading edge will be flat. So you have your normal shock waves that are generated on the conventional airfoil here. For a supercritical airfoil, it will be further aft from the leading edge. So your flow separation, all of that are pushed further aft. So this entire region is capable of producing lift. Then you have reduced boundary layer and shock interactions. Again, the same reason, because your shock is formed later in time, like later for a larger period of time, larger period of angle of attacks or flow. Also, it is formed aft. So it gives you a larger range of operation. And when there is a lesser interaction between the boundary layer and shock, you have less drag. Then what happens is that since there is a flat upper surface, the end wing ends up thicker. Thicker wing implies lighter wing. Why? If you think about it logically, thicker wing should be heavier, right? But thicker wing implies lighter wing in aircrafts. Why?
Ma'am, because it will be hollow from inside, ma'am. So
Yeah,
because of being hollow, it is lighter in weight.
Correct, exactly. So if it's hollow, if it's a thicker wing, you need less structural reinforcements to make it withstand the loads. So in effect, you have lesser reinforcements and it becomes lighter. And it is hollow. He's right. So hollow wing is more structurally strong when you have the loads considered on it. So you don't need more structural reinforcements. So the wing becomes lighter. Right? So yes, this is the figure that I was telling. Initially, we had seen these three figures in the previous slides, where the initial flow, if it's less than the Mach number, less than the critical Mach number, it flows smoothly over the surface. Even when it reaches just before the critical Mach number, it is fine. When it crosses the critical Mach number, you have a normal shock wave formed here. and a possible flow separation near the trailing edge. It starts, it's between turbulent and laminar. You can only say possible flow separation. Right? You have supersonic flow ahead of this. That is, this is formed at Mach 1, so you have supersonic flow ahead, and after of it is subsonic. Then when it goes further beyond, you have a similar shock wave formed at the bottom surface. And this shock wave travels aft, and there's a definite flow separation at the trailing edge. When it flies at higher speed, the condition becomes much adverse, and the normal shock wave is detached at the trailing edge, and the entire flow, you can see it's definitely separate. And when it goes further, you have a bow shock and then normal shock waves formed at the leading edge. Okay, so as you go further from the critical Mach number and the Mach 1, the flow becomes adverse and it becomes undesirable flow. Okay. Okay, so we'll just begin with the questions of assignment 3. I hope all of you have solved the assignment 3, right? We'll just go over the questions. Okay. So what will be the total fuel fraction for X number of mission phases? Okay, so let's write this down. So suppose you have the weight required to fly for X missions is Wx. So initial weight was W0 minus Wx. So that is the amount of weight you require to fly for X missions. By weight fraction, how do? You divide it by the initial value. What does this amount to? 1 by Wx by W0, right? So that is this. Wx is the amount of fuel that you require to fly for the X missions. Then we have, which of the following is not an application of an airfoil? Does the airfoil provide lift? Yes, it does, right? So we know our CL versus alpha graph. The airfoil definitely provides lift. It provides lift coefficient is equivalent to it provides lift. Does it provide thrust for acceleration? Does the the airfoil, does it provide thrust for acceleration?
No, ma'am.
No. What provides thrust for acceleration?
Engine.
Engine.
Does the airfoil ensure streamlined flow?
Yes,
Yes.
it does.
What is streamlined flow?
When the flow flows in laminar.
Yeah, so
Laminar.
in parallel lines, when there is no interaction between the different layers of the fluid, laminar streamlined flow. Yeah? So the airfoil ensures all the others except for thrust. So this is the right answer. Does not provide thrust for acceleration. Which of the following is not a type of airfoil?
Vortex, ma'am.
Vortex. What is vortex?
A vortex is like a twisted air stream which swirls around.
Okay. Okay. Yes, it's correct. Yes. You have various types of flows: source, sink, vortex. Vortex is something that swirls around, like he said. Sink is where everything flows into a point, and source is where everything emanates from a point. So this is vortex. This is sink. This flows. They are just different types of flows. They are not types of airfoil. We have symmetric, camber, and reflex. What was the purpose for reflex airfoil? We just discussed this in the first slide, I think. What was the purpose? Why do we require reflex airfoils? What are reflex airfoils?
Which have their
Ma'am,
camber line cut across the chord line.
Okay, correct. Okay, so you have a slight upward bend towards the trailing edge. Why do we need this?
For positive CM0.
Exactly. Positive CM0 of the wing. So we'll just go over just conventional airfoil designs that are encountered. So first we know that this is a symmetric airfoil. This is what we begin all of our discussions with, symmetric airfoil. Then we have a low camber. Low camber is where the flat bottom is there and there's a slight curve above. So this ensures camber itself is for increasing the lift. Okay, so this ensures low drag and high speed, and overall the wing is thin. Right? Then you have deep camber or like high camber, which you have a higher curve in the upper surface, but still a flat bottom. So you have high lift here, low speed, and a thicker wing section, obviously. Then when the lower surface is also cambered, it has characteristics similar to these. These two have similar characteristics. 2 and 3 have similar characteristics. It's just that the lower surface is also cambered. Okay. Then you have, this is the reflex airfoil, right? Reflex. This is what he said. That was a good definition where the camber line cuts across the chord line. The chord line joins the leading edge and the trailing edge. The straight line joining that. Camber line would be something like that cuts across that. That was a good definition. So a reflex airfoil, it has lower lift compared to the other cambered airfoils. It also has higher drag, but we require this, we bring this into play to ensure that you have 0 or positive CM, not CM at AC, okay? That is required because we require our aircraft to fly. We don't need any moment gets carried to the aerodynamic center. We also require our aircraft to be trimmed at positive angles of attack. We prefer our aircraft to be trimmed at positive angles of attack. Then you have, this is the supercritical airfoil that we were discussing. Supercritical. So you can see that the top surface is more or less flat, and then when it reaches the trailing edge, that is when the camber is introduced. You can see that it is thicker, just like we had discussed. Thicker means lighter wings. And what is the purpose of supercritical airfoil? Main purpose?
For increasing M critical and M drag divergence.
Correct, absolutely. Okay. Next question for the airfoil NACA 0012. What does 12 signify? This is the 4 series aircraft.
Thickness.
Thickness, yes. It signifies thickness. What will be the exact value of thickness? It will be
0.12 C.
I just pasted the slide from the digits signifies the thickness in 1/100th of C. And this is what we got as 0.2 C, 0.12 C. Next, the choice of lower thickness to chord will result in, we discussed this again,
Higher critical max.
higher critical Mach number. Exactly. So for CL max, how CL varies with, CL also varies with thickness to chord, but you can't definitively say if you lower T by C, how will it look? The CL max is like this. Okay, so you cannot definitively say if you reduce T by C, will CL max increase or reduce. But for critical Mach number, the graph is shown here. You can definitively say that this is T by C. Okay. When C is reduced, your critical Mach number is increased. Okay. Then, what was the other characters? Okay. What ensures higher stall angle?
Flat.
Sorry, a higher flaps. Yes, it's a CL max. Okay, high lift generating device. But if for just a plain airfoil, what we discussed this
Camber
camber.
section, ma'am.
Yeah. So you have an airfoil like this. For a lower aspect ratio, your airfoil will look like this. Camber also, he's right. But for a lower aspect ratio, your CL versus alpha graph keeps, your slope keeps reducing, keeping all other parameters same. So if you have aspect ratio equal to 10 and this aspect ratio equal to 5, aspect ratio equal to 1. So this goes on increasing your alpha stall or CL max. CL max is same, but it pushes it across the graph, which increases your alpha stall. So all other parameters are retained, just the alpha stall is increased. The aspect ratio and camber, both of them contribute towards increasing stall angle. Okay. This question we have been doing several times. This was there in your assignment. So one of you tell me how to proceed. What is the equation?
V stall equals to under root 2 times the weight divided by rho CL max
Yes.
into S.
Just substitute the values and tell me the answer.
61.72.
Just write this down. is 13.2 comes to 61.72 meters per second. What is this? Okay. Next question for a cambered airfoil, Cm naught is,
Negative.
Negative.
and you have a reflex airfoil to make it positive. And for symmetric airfoil, it is 0. This is symmetric, this is cambered, and this is reflex. Trim a flying wing at positive angle of attack. Which of the following arrangements is done? We just discussed this.
Reflex.
What determines the longitudinal stability of an airplane?
Location of CG with respect to
Location of
neutral point.
CG with respect to
With respect to neutral point, yes. So what if for a stable aircraft, if this is your fuselage reference line and this is your neutral point, where should the CG be?
Ahead of neutral point.
Ahead of neutral point, yes. So CG should be here. This is for a stable aircraft. And if it is at neutral point, how can you comment on the stability?
Neutrally stable.
Okay, so if it is subject to some disturbance, how will it behave? Suppose it's flying at some pitch angle and it's subject to some gust. It is now at an angle of attack 5. How will it behave?
it
It
will
will-
try to control its angle of attack, ma'am. Means it will pitch down if it goes pitch up movement, ma'am.
If your CG is at neutral point, how will it behave?
It will
Then it will
push downwards.
Will it push downwards?
no, ma'am.
No.
It will attain an equilibrium position at
Yes.
if
So
there
it will
is 5-degree angle of attack.
exactly. So it will assume a new equilibrium position at 5-degree angle of attack. So what Achyut was saying, that condition is for when the aircraft is stable. That is when CG is ahead of neutral point, it will try to regain its original equilibrium point of 0 degrees. But if your CG is at neutral point, it is neutrally stable. What this says is that it will assume a new equilibrium point and try to remain there. So this is from the similar same example that we start with when we do stability analysis. If there's a ball and you have a ball here, you subject it to some disturbance, it will come back to this point. So this is stable, statically stable. And if you have a upturned bowl and you have a ball on top of it and you subject it to some disturbance, it will just keep going. It will have no tendency to return back. And if you have a ball on a flat surface, and if you subject it to a disturbance, it will move to the new position and it will remain there. It will not come back to its original position, neither will it go away from this position. So what we can say is that it will attain a new equilibrium point. That is neutrally stable. That corresponds to when CG equal to NP. XCG equal to NP. Okay. Now this is just a few set of questions other than your assignment 3. Which placement of wing has least lateral stability?
Low wing.
Why?
Ma'am, we cannot say no, ma'am, because it actually depends upon the aircraft.
Okay, why? Okay, someone who said low wing. Why did you say low wing? Can you try to explain?
Because ma'am, if no dihedral or anhedral angle is given, if it is subjected to any lateral wind gust, then one wing stalls more than the other in the opposite sides of the gust direction.
So I'll just try to draw and explain. I'll just try it. So first I'll take the high wing case. So if you have a high wing and suppose it has turned like this, okay? Then the oncoming velocity will hit. There will be a normal component of the velocity in this direction. There will be some component of the velocity in this direction, which produces a moment, restoring moment. So it will try to regain its equilibrium point. This is for the high wing case, right? So you have a
Yes,
restoring
ma'am.
moment created. So the same thing, you have a low wing. If you have a low wing case, and for the same orientation, this normal component will now act here. The effective normal component will be here, and you will have a component here. So there is a lift produced here, which produces a further destabilizing moment. There is no restoring moment produced. So if it's a low wing, it will continue to roll in the direction of the disturbance. It will not try to regain its equilibrium. Okay. So someone who said that it depends on aircraft, is this clear now?
Yes, ma'am.
Yes. So the low wing has the least lateral stability. High wing is inherently stable. And just like I'm sorry for the name, Rupender, I think, like just like he mentioned, for a low wing, if you have a dihedral angle, you have something like that. This is laterally stable. It contributes towards lateral stability. Okay. So I have a figure here that shows just what we said. So when it rolls here, when this is high wing configuration, when it rolls towards this side, there is a lift produced here, which is higher than the lift produced on this wing. So it produces a restoring moment and it tries to regain its original equilibrium point. When it's a mid wing, production of the lift is same and it's neutral, it's neutrally stable, right? And if it is a low wing, you have a lower lift produced here than the lift on this wing. So there is an adverse moment, not a restoring moment. It will continue to roll in the direction of disturbance. Okay. Here I've just summarized the terms that are used to denote stability in the three directions. So for longitudinal stability, that is in the pitch axis, you have Cm alpha and you require Cm alpha to be less than 0. What is the term that contributes? What is the geometric, geometric property or the structure of an aircraft that contributes towards longitudinal stability? Is the horizontal tail. Horizontal tail is what ensures that you have Cm alpha less than 0. For directional stability, the derivative is Cn beta, and it should be greater than 0 for directional static stability. And the component that contributes towards this stability is the vertical tail or a swept back wing. And for lateral stability, just like we've seen now, Cl beta, that is the derivative, it should be less than 0. And the components that contribute towards lateral stability are high wing, or if it's a low wing, dihedral angle, and vertical tail, obviously. Okay. So this is a summary of all the derivatives that denote stability in the three directions, denote static stability in the three directions. Okay. Now, determine the corrections or otherwise of the following assertion and reason. So statement 1 says that most of the tails are using symmetric airfoils. Is this true?
Yes, ma'am.
Yes. Why do most of the tails use symmetric airfoils?
Because we don't
Ma'am,
want
because
any
it-
unwanted force.
I couldn't hear you. Can you just repeat yourself?
Ma'am, because it doesn't produces any thrust or unnecessary.
Thrust. The airfoil doesn't produce thrust, right? It produces lift. It does not produce. We want symmetric airfoil so that it doesn't produce any unbalanced lift, right? Not thrust. Thrust is, like we discussed in the previous question, thrust is engine. Engine produces the thrust. The airfoils produce lift. Okay. Okay. So the first statement is true. Now, tail control has two primary control surfaces. Here they just said tail. They didn't say horizontal or vertical. So does the tail have two primary control surfaces?
Yes, it has.
Yes. So the horizontal tail has elevator and the vertical tail has rudder. And they mentioned primary control surface. What would a secondary control surface be?
Like our high lifting devices and flaps, spoilers, tabs.
Tabs. Yes. Trim tabs are the secondary control surfaces. High lift devices, though they look similar to the control surfaces, their primary purpose is to increase the lift.
Ma'am,
Your
but spoilers can be secondary.
spoilers can be, yes, spoilers can be used to control. That's true. So trim tabs and spoilers, they are the secondary control surface. But the primary control surfaces are for horizontal tail, it is elevator. And for vertical tail, it is rudder. So this statement is also true. So now let's look at the options. Both A and R are true, and R is the correct reason for A. Is that true?
Both are true, but
Yes.
B is not the
That
correct.
is not the correct reason for A, ma'am.
Exactly. So this is wrong. This is the correct one. Both A and R are true, but R is not the correct reason for A. Correct.
Ma'am, can you please just show the previous slide, ma'am, in which you were saying about the stability,
Yeah.
directional stability, longitude?
Yes. Did you have a doubt? Is there some question in the slide? Did you have some question?
No, ma'am, I'm just taking a screenshot of it, ma'am.
Okay. Okay, just let me know when you're done. These slides are made available to you, right? Do you get these slides? Can someone just confirm if you are receiving the slides?
Actually, don't know, ma'am. I don't think that we can see these recordings.
The recording is made available to you, right? You have the YouTube link is given to you.
Ma'am, no, ma'am. For this out session, no YouTube link is available. Only
Oh,
the hosts or lectures are available.
okay, just a minute. Let me just check that. We'll come back to this. Just a minute.
Ma'am, I only got a link of the first 2 sessions, ma'am.
Yes, we only had 2 sessions so far, right?
Previous one, we didn't get, ma'am, because this is the 3rd session which is happening.
Yes, so you got the link of the first 2 sessions, right?
Only the first session, ma'am, not for the second one.
Okay. I've put the link in the chat box. This will be the same playlist to which I'll be uploading, so you can keep referring to this. I was not aware of this. I think I'll give you the links to the drive in which I upload the slides also. Let me just look into that. Where I'll be uploading all the slides and the first playlist. This will be the same playlist and the same drive where I'll upload the videos and the slides. Okay. I did not know that you were not receiving it. Okay. Let's get back to us. Okay. So you're done with this slide, right? Archit?
Yes, ma'am, I'm done, ma'am.
We'll move ahead. To maintain static stability and trim for wing canard aircraft. So what is a canard?
It is a tail, but it is connected ahead of the wing.
Exactly. Okay. So for a wing canard configuration, to maintain static stability and trim, that's not, okay. The location of center of gravity. Should it be
B.
the wing? Yes.
B option.
Center of gravity must be between the wing and the canard. Yes. So let's just look at if it's a simple wing configuration, if it's just a wing, your AC is what we take into consideration here, aerodynamic center. So your CG for a simple wing configuration should be ahead of your AC. That is when your simple wing is stable. So when I had done a course on stability control, one of the simplest exercises that the professor had made us do was to take any rectangular piece of thermocol or anything, just take a rectangular piece and try flying it. It will just flip over. Then try adding a weight, progressively keep trying adding a weight at the center line in the front. So if you have a rectangular surface here, at this point when there is no weight added, your CG is at the middle. Now, if you keep adding a weight ahead, if you keep adding weight here, at some point your CG will go ahead of the aerodynamic center, which is usually at the quarter chord point. So if you keep adding weight here, the CG moves ahead and at some point it will cross the AC. And at that point, when you try to fly this plain sheet of thermocol, it will not tumble, it will smoothly fly. You can just try this at home. Our professor also made us do a wing tail configuration. You can try that. Okay. So your CG should be ahead of the AC for just a wing alone configuration. for stable flight. Now, if it's a wing tail configuration, when it's just a wing, your aerodynamic center is where we base all our calculations on. When you have an aerodynamic center, when you have a wing and a tail, you have neutral point. Neutral point of an aircraft is analogous to aerodynamic center of a wing. So neutral point has the same properties. So your CG should be ahead of the neutral point for a stable aircraft. Now, why does this neutral point shift backwards? It initially, if it's just a wing, your neutral point and AC are the same thing, right? So when you add a tail, why does the neutral point shift backwards? Because you have another aerodynamic component added towards the aft, right? So you have another aerodynamic component that produces these aerodynamic forces. So your neutral point is pulled backwards. Now, like he said, the canard is just like a tail, but it's added ahead. So it'll be ahead in the fuselage reference line. This will be your canard. So if you have a neutral, if you have an aerodynamic component that is added ahead of your wing, the neutral point will shift forward or backward. When I added a tail, it shifted backwards. When I added a canard, where will it shift?
Ahead.
Ahead, exactly. So your neutral point will shift ahead. Now CG has to be ahead of neutral point for all any configuration for it to be stable. So if your neutral point shifts ahead, your CG should also move ahead for stable configuration. So let's just look at that. So neutral point you can see has shifted ahead, and CG has to be, we have to move it forward to ensure stable flight. So the correct option is what he has said. It should be between the wing and the canard. This is the location of CG. So canard is just like a tail that is added ahead of the wing. Okay. Next question is, if the aircraft tail volume ratio increases from 0.45 to 0.55, what will the change in the stall speed of the aircraft be? What is tail volume ratio? What is the, how do we denote it? R convention?
VH.
VH. And what is it equal to?
LT
EST.
divided by SW C bar W.
Yes, correct. So LT is the tail moment arm, ST is the area of the tail, SW is area of the wing, C is the mean aerodynamic chord of the wing. So if I increase this VH from 0.45 to 0.55, will the stall speed of the aircraft increase, decrease, remain same, or will it, can you not say? Stall aircraft speed.
It shouldn't be affected, ma'am.
Exactly, correct. He's absolutely right. So the stall speed, we know the formula. We've been using this several times in this course. 2W by rho SCL. There is no VH here. I'll just summarize that here. So the VStall, this is the formula. There is no VH here. You don't see any VH. So changing VH will not change VStall or alpha stall, will not change CL max. It will not affect that at all. What will it affect? It will affect the stability. Where do you see VH here? You have VH here and here. And this is the CM naught contribution of the tail. This is the CM alpha contribution of the tail. So VH, changing VH affects these two parameters. Increasing VH increases the CM naught contribution of the tail, and increasing VH reduces, contributes towards a lesser slope, steeper slope. So VH only affects the stability, longitudinal stability. It does not affect the stalling speed. Okay. Next, the pitching moment coefficient about the leading edge of an airfoil is given by this equation, where alpha is the angle of attack of the airfoil in degrees. Trim angle of attack for airfoil in degree will be. What is trim?
To fly the aircraft at any other angle of attack, at trimmed angle of attack, we can say.
Yeah, what is this trim? What is trim?
It is the point where the CM and the CL or alpha slope cuts the x-axis. It is
Okay.
also that point.
Okay. Can anyone else try to answer? What is trim? Question is, what is trim? Anyone else? Just try. Okay, so what he said was where the CM versus alpha or the CL versus alpha. CL versus
No,
alpha.
ma'am. It is CM versus alpha or CL. It can be
Okay,
alpha or
okay.
CL.
Okay, okay, fine. Where it cuts here. So what it means is that trim is the equilibrium point. Okay, where your total sum of the moments equals 0, sum of the forces equals 0. That is your trim. So you're right, it's where CM cuts the x-axis, that is where CM is 0. So for this case, if your CM is 0, that is when you have trim. So what will alpha trim be?
5 degree.
That is nothing but 1.9 by 0.0298. That is 5 degree. Okay. So next question is, when the angle of attack decreases, the moment of center of pressure will be towards trailing edge, independent of angle of attack, towards leading edge, or all of these.
I think it is towards the trailing edge.
What's the trailing edge? Okay. Can anybody else try to answer? It's always him that's answering. Anybody else just try it. Okay, if I tell you that what he said is right, it moves towards the trailing edge, can you try to justify it? Anyone else? I'm not saying that it's right. If it is right, can you try to justify it? Come on, one of you just try. What is the center of pressure? Can somebody tell me?
The point at which all the aerodynamic forces act.
Exactly, exactly. Absolutely right. So will it move towards the angle of towards the leading edge or trailing edge when angle of attack increases?
Towards the trailing edge itself, ma'am.
Towards the trailing edge. Can you try to justify why?
Yes, ma'am. The reason so is because, ma'am, if we see through the diagram, ma'am, if the angle of attack increases, it usually hits the leading edge, ma'am, first, if it's more.
Yes.
But as we'll be decreasing the pressure, the angle of attack, it will start moving towards the trailing edge, ma'am.
Angle of, okay, well, let me just try to understand what you said. So at this case, this is the chord line. And suppose your free stream velocity is also in the same direction. What is the angle of attack here?
If it's what to say, high angle of attack, ma'am. So it will
Here.
first touch the leading edge.
What will first touch the leading edge?
The angle of attack, ma'am, means the pressure which will be trying to push it forward, ma'am. So it will first hit the leading edge to
Okay, so
create the angle of attack.
velocity or the free stream, the air basically will hit the leading edge first. Okay. So when I increase angle of attack, what happens? This is your mean chord line, and this is your free stream velocity. And this is your angle of attack. What happens now? You're right. When if it is 0, it hits the leading edge first, right?
Yes, ma'am.
And when I increase the angle of attack, what happens? So if this is a symmetric airfoil, can you tell me how the pressure distribution above and below will be?
Ma'am, above and below will remain the same, ma'am, because it does not create any thrust or upward movement.
Yeah. Okay. So you need to be careful when you say thrust. It's not thrust. Okay. It's lift. Okay.
Yes.
Okay. Yeah. It's lift, not the thrust. Thrust is in the engine direction. That is in this direction. So your lift and drag are generated perpendicular to your flow. Lift is perpendicular and drag is along the flow. Okay. So if it's a symmetric airfoil, 0 degree angle of attack, no lift is generated. But will drag be generated? symmetric airfoil, alpha equal to
Yes,
0.
ma'am, there will be
Drag will
drag.
be generated.
Yes.
Skin friction mainly or
Profile drag, we can say.
profile drag.
Yeah. So your drag equation, the CD is equal to CD naught plus K CL square. This will be 0, but your CD naught will be there. Right? So
Yeah,
drag,
the parasitic
even if
drag.
yeah, exactly. Parasitic drag. That's correct. So now let's come back to our original equation, your question. When I increase angle of attack, what happens? You were right. You said that at 0 angle of attack, it hits the leading edge first, and the pressure above and below remains same. There is no effective lift. All that is right. Then when I increase angle of attack, what happens? Where does the velocity, where does the oncoming airflow hit? Or can someone tell me how the pressure distribution about this airfoil will be at a positive angle of attack?
The flow will accelerate above the aerofoil, but will also separate early. On down, there will be positive pressure, high pressure.
Yeah, so here there will be something like this. This will be negative and this will be positive. It will be lesser. Okay, it will be above, but like this is positive, this is negative. He's right. This is negative, and this is positive. Positive below and negative above. So where do you think the center of pressure for this configuration? Let's assume that it's at this location. For symmetric airfoil, center of pressure, aerodynamic center are the same point. For this configuration, where will center of pressure be? If initially it was here, now where will it be? Does everybody agree with the pressure distribution that I drew here?
Yes, ma'am.
Yes. So initially when it was equal above and below, your center of pressure was here. Now that it's unequal, the distribution is unequal above and below. This was the original CP. Now where will the CP be?
Move ahead.
Ahead. Exactly. Why? Because you can see that the net pressure is higher. The net pressure is higher above, the magnitude is closer to the leading edge. Similarly, when I reduce the angle of attack, your chord line is here, and oncoming velocity is here. You have a negative angle of attack. Now, how will the pressure distribution be?
Negative below and positive up.
We'll have something like this, negative below and positive up. Will be something like this. So if your original CP was here, now where will it be?
Ahead, near the leading edge.
Near the trailing edge. Yes. The answer is right. When the angle of attack decreases, your center of pressure moves towards trailing edge. Did everybody understand this? We'll just go over this figure. But at some positive angle of attack, you can see the pressure distribution here. Blue is a negative and this red is positive. Okay. So you have a negative pressure gradient above and a positive pressure gradient below, which is what produces the lift force, which is what produces the aerodynamic force. So if your CP is somewhere here, where the net pressure is high, so that now when I increase angle of attack further, when I make it 10 degrees, you can see that this curvature or this gradient moves towards leading edge. So your CP that was initially somewhere here now moves here because your equilibrium, your net pressure distribution has moved towards the leading edge. So CP has moved to this location. Now your lift force is represented at this point. And drag. And when the net angle of attack is reduced, when it goes to -8, your original CP was somewhere here, and now it has gone here because you can see that the pressure distribution has moved towards the trailing edge. Keep in mind that this pressure distribution, though it shows an upward arrow, it is negative, which is why the flow accelerates. Okay, so there is also a positive quantity here, this denoted in red, which is what generates a reduction in lift. Okay, so there is there is a net lift downwards at the sea. Lift and drag. I cannot say lift. There is a force downward. Okay. Is that clear now? Do you understand how the center of pressure changes? The
I'm
one,
still a bit confused about the negative angle of attack. CP still
just-
moves behind.
can you just repeat your question? I didn't get you.
I'm confused in the negative angle of attack case. CP
Okay.
moves behind.
Yes.
Then shouldn't it be moved ahead as well?
So your pressure distribution, the net pressure distribution will be about this point.
And
Right.
the aerofoil is same, the positively cambered aerofoil.
Yes, same airfoil.
Okay, that now I can understand.
Okay. So there is a positive quantity here, but it is less compared to the negative properties. Okay. You see why it moves backwards, right?
Yes, ma'am.
Okay. What about the others? Are you convinced with this explanation? Do you see why it moves towards trailing edge? The others, the other participants, is this clear? Do you need me to go over it again? Is this clear?
Just one in short, once again, can you explain?
Okay, yeah, sure. So I'll just get rid of all these. I'll just draw it again, just a minute. Okay. So now here it says center of pressure is here at this angle of attack, at a positive, a small angle of attack. Your net pressure, the pressure distribution above the surface is denoted by this curve, and below is denoted by this curve. Below it is positive and above it is negative. But your net pressure distribution seems to act about this point, right? So that is your center of pressure. And that is where we denote our aerodynamic forces. Now, when the angle of attack increases further, there is a pressure distribution that moves towards the leading edge. So now you can see that your net pressure distribution has a value at this point. Okay, so it has moved towards the leading edge. The higher pressure gradients has moved towards the leading edge, which is why your CP has moved ahead. So now we represent our aerodynamic forces about this point. Similarly, if it moves downwards, this positive pressure that was below the airfoil surface is now it has now traveled above the airfoil surface. So there is a small quantity that is above the airfoil surface, and the other quantities move backwards. Now the net pressure distribution happens at a point that is towards the trailing edge. It has traveled backwards. Okay. So that is where we represent our aerodynamic forces. Now, do you see why we don't take the center of pressure as the reference point for all our measurements, all our analysis? It keeps moving
Yes, ma'am.
throughout the flight, right? So it becomes difficult for us to denote our aerodynamic forces, which is why we've come up with a point called aerodynamic center, which remains same throughout the duration of the flight, does not change with angle of attack. Okay, that is, in fact, that is how the position CM is defined. AC is defined. AC is the point that does not change with angle of attack. Now, one of the airfoils that we discussed, one of the conventional airfoils that we discussed, had very less variation of CP with angle of attack. Do you remember which one that was? It's obviously not cambered airfoil or symmetric, because we saw just now that it's changing very much with change in angle of attack. One of the conventional airfoil cases, we had mentioned that it's the change of pressure distribution, or the change of center of pressure is very less, very minimal changes. Do you remember which airfoil that was? Let me just go back to that slide.
The critical.
Let me just go to that slide. Where you had seen a very little movement of center of pressure. It's the reflex airfoil. Okay, that is another advantages or good quality of the reflex airfoil. Though it has low lift when compared to cambered airfoil, it has certain good qualities, which is why it is used in some cases. Okay, so very less moment of center of pressure, very little moment of center. Okay, so this is just the plotting of the graphs. I'm sure all of you have done that course or some experimental course where you have plotted the CP with respect to x by c. X by c is just the position with respect to chord along the chord. So for all graphs, we have taken the positive quantities above and negative quantities below. But for the center of pressure, we tend to plot it in this way, right? So that you have the upper curve representing the upper surface and the lower curve representing the lower surface. So now you can see at 0 degree angle of attack, the net forces, the net pressure, the CP is highest at this point. And since it's a symmetric airfoil, the pressure above and pressure below are same. So the curves coincide. Both curves are about on the same line. Now, when I increase angle of attack, the curves are not at the same point because your pressure distribution changes. So this is that curve that we've seen. Right? So the pressure below is positive and the pressure above is negative. This is negative, this is positive. And you can see the change in the graph here. The upper surface, higher negative values, and the lower surface, lower positive values. Okay. And this is just a nice animation that I found. I thought I'll share it with you. After you see this, do tell me what is not correct in this animation. Okay. So there are 4 different simulations that are shown here. First of which is this. What does this show? This one. What does this show?
Like blue region is the negative pressure, red is the higher pressure region.
Yes. So you can see how it varies when you change angle of attack. Okay.
Yes, ma'am.
Yeah, and you can see the streamline flowing above and below the airfoil. Now the next simulation shows you another parameter. Look at that. What do you think this shows?
Magnitude of the pressure, CP.
Okay, it tends to follow the same pattern, but this actually is showing your normal forces. You can see they're all perpendicular to the chord. So this is the net normal force. Okay. But yes, it follows the same pattern as CP. You're right. Now just look at the next graph, next simulation, which will start in just a while. Yes. So now what is this? So there were actually 4 simulations. One was this red and blue color simulation for center of pressure. Then this distribution was the normal forces. And it's not, the transition is not clear, but there is another. So right about now. Yeah, so that. Sorry. This is the normal forces. Then you have lift CL is shown. And what is this? So normal force.
No idea, ma'am.
Okay, normal force and CL were more or less the same pattern. Any guesses as to what this is?
On drag, it shows drag.
Yes, it is the drag. It is the drag. Change in the angle of attack. I mean, drag with change in angle of attack. Okay. So now in the first simulation, there was actually throughout the simulation, there is a problem. Can someone tell me what is wrong? It's a beautiful simulation, but what is wrong? What can someone?
Maybe it is not showing the flow separation.
Exactly. So there is no flow separation happening here. And here we're assuming laminar flow throughout. But at this point, there will actually be some vortices, right? And which travel backwards. So that is not shown here. We're assuming laminar flow, not a turbulent flow. So that is the problem with this. Otherwise, it's a very beautiful simulation. I just wanted to put it here. Okay. So now some questions from NACA airfoil series. So this is a 6 series airfoil. What is the location of minimum pressure from leading edge? I don't think we remember what is the, this is the, from the first slides. The location of minimum pressure is given here.
0.3 answer.
Point-
Third.
0.3C, location of minimum pressure. Okay. So let's just try to find out the other parameters also. The load drag is maintained in 1/10 above and below design lift coefficient. So in this case, what will the value be? The subscript is 3.
0.3. It is.
So that will be 0.3 plus or minus 0.3 from CL design. That is where you have low drag or favorable conditions maintained. Then what is the design lift coefficient? In this, I think there is a problem with this because it's just 0.
0. Yes, ma'am.
So I think it is a problem. Can 0 lift coefficient be there?
For a symmetrical aerofoil, we can say
CL not is 0. Yes, correct, correct. So you have 0. So CL design is 0. Then maximum thickness.
0.180.
See, correct. Next question is the maximum thickness to chord ratio, which we have already found out as 0.18. Okay. Then for an aircraft to fly at design CL of 0.6, because when it just says CL, it's design CL of 0.6, which is the most suitable airfoil?
Third.
Third. Why? Which was the digit that signifies CL design? Third is the correct answer. Which was the digit that signifies the CL?
Third digit.
Third digit, yes. So 6. So it is in 1/10 of the chord, so it will be 0.6. So for the first case, what is it? These are 5 series, and these are 6 series. For this case, at least for the 6 series, what will it be? Again, it will be 0, right?
Yes.
Are the other participants following?
Yes, ma'am.
Yes, okay. Anybody has any question, do stop me. We will go over the questions again, okay?
Okay, ma'am.
So, what about the first case? What will the design CL be?
0.
Okay. Let's just look at it. Design CL for the NACA 5 series is the first digit multiplied by 1.5 in 1/10 of C. So it will be 2 into 1.5 by 10 C, which is
0.3.
0.3, correct. For the second case, for this case, what will be the value be? Just follow the same sequence.
Point 9.
Exactly. So it'll be 6 into 1.5 by 10 C, which is 0.9. Why aren't the others answering? Are you following?
Yes, we are.
Okay, okay. Just stop me if you have any doubts. So the other two cases are fairly simple. Okay, let's go to the next question. A propeller-driven aircraft having fuel weight of 650 kgs. Now the aircraft is taxiing on the runway, after which it has a fuel fraction of 0.975. Determine the fuel left after taxiing the aircraft. How will we go about doing this? Just tell me, we have done several questions of this pattern. Can you just tell me, how will we go about doing this? Just somebody try, attempt.
Ma'am?
Yeah.
W0 is the total takeoff weight, na?
Yes,
Including the
yes.
fuel.
Exactly, yes. Okay, so your initial fuel WF1 was 650 kgs.
Answer is second option, 125.
Okay, can you tell me the steps that you followed?
Just multiply the weight fraction by the total weight
Ah,
and
Subtract.
subtract 1.
Exactly. Can anyone else tell me how the correct answer is the second one? Can anyone else tell me how he might have arrived at it? Anyone else just tell me. Now you have the correct answer, just tell me how we arrived at that. Just come on, tell me, just anyone, just tell me. Or just try guiding me through it. We'll just see. So the value given to us, the first, how much fuel is available is 650 kgs. Initial weight is 5,000 kgs. What will the next step be? What is this 0.975? What is given to us? So
Fuel fraction.
Yes. Initially it was W naught. Then it minus how much fuel you consumed.
Ma'am, actually fuel fraction is weight of the fuel upon the total weight.
Yes. So
So it is 0.975. Isn't it a very large number
it's
for fuel fraction?
1 minus 0.975. This is the
It
value,
is
right?
the remaining fuel fraction.
Yeah, it's the remaining fuel fraction.
Acha.
So your delta W by W naught is 1 minus 0.975. Right? So delta W is delta
W naught into 1 minus 0.9. Or we can say W into 0.025.
okay. W is 5,000 into 0.025. Right?
Yes, ma'am.
Yes. So how much is this value? Can someone just calculate and tell me?
So ma'am, the answer must be option 4, na? Because this is
Okay,
coming
so
out.
yes. 125 is how this is 125, right?
This is 125, yes. So the fuel left will be 525.
25. So fuel left will be 650 minus 125, which is 525. Yes?
Yes.
Okay. Along similar lines is this question. Look into it. An aircraft has a gross weight of 1,700 kgs. At the end of the mission segment, it has a weight fraction, not fuel fraction, weight fraction of 0.9. Determine fuel consumed during this mission. Along similar lines. So initial weight is 1,700 kg.
170 kgs.
Okay, let's just go through it. Okay. Can you tell me the next step?
And that Wx by W naught is given as 0.9.
Wx by W naught is given as 0.9. Then
So the fuel fraction Wf by W naught will be
WF.
equal. Ma'am, 0.9 is Wx by W naught, na, the mission segment fraction.
So that's the delta W, right?
Yeah, we can say that.
Okay, fine. Wx. Okay. So this will be will just be 1 minus 0.9
Yes.
into the original weight.
Yes, ma'am.
So that is 170 kgs. What about the others? Did you follow these last two questions? Okay. I don't think anybody has a question. So, okay. So we come to an end of this session. Does anybody have any questions from this session or anything else? In this entire session, do you have any questions? Anybody else? I know 2-3 people have been interacting, but the others have not been interacting. I'm not sure if you're following. Okay, somebody has asked me to explain what Arun Siva, what do you want me to explain? Okay. Any Okay, you have understood. Okay. Anybody else has any other questions in this entire session? All the questions that we discussed, any questions? Okay. So I think we'll stop this session here if you have no questions. Do
Ma'am,
go
I have a doubt in one question of assignment 3. I couldn't follow up. Just
which
1
one?
minute. Ma'am, it was question 8 of assignment 3.
Okay.
Yes.
Okay. So this is what we had discussed. So let me just draw this. For a symmetrical airfoil, your center of pressure and aerodynamic center are at the same point. So Cp equal to AC. So your aerodynamic forces are represented at that point itself. So this is drag, this is lift at that point itself. Okay. Now for a cambered airfoil, for a positively cambered airfoil, you have something like this. Your Cp is somewhere here. This is Cp, and your aerodynamic center is here. So your aerodynamic forces are represented at Cp, that is lift and drag. But since we saw that the Cp changes with angle of attack, we picked a point that is convenient for our analysis that does not change with angle of attack, which is the aerodynamic center. So now when we represent our aerodynamic forces at this point, we transfer the forces. We transfer lift and drag here, but it also comes with a moment. Okay, so it comes with a moment and nose down or a pitch down moment in this case. So your Cm, that is the pitching moment at AC, is negative. Okay, here in this case, CMAC is 0. There is no moment at this point. It only comes later when the tail lift force are generated. But at this point, for a symmetrical airfoil, there is no moment. There is no pitching moment. But for a cambered airfoil, you have a negative or pitch down moment happening here. Now, this is undesirable. So we wanted to have a positive angle of attack. Why do we want it to have a positive angle of attack? So Cm versus alpha graph is something like this. Okay. So this is the point of trim. Like trim is sum of all moments equal to 0, sum of all forces equal to 0. So this is the point of trim. Now, if we had a line like this, your trim would happen at a negative angle of attack. So your equilibrium point will be at a negative angle of attack, which is not desirable, right? You cannot have a trim at a negative angle of attack. You want it to be at a positive angle of attack. What do you change for that? You don't change your slope. So Cm alpha does not change. What changes? Cm naught changes. So at this point, Cm naught is negative. At this point, Cm naught is positive. So if we have to trim at a positive angle of attack, your Cm naught has to be positive. Okay. But if you take a cambered airfoil, it is beneficial for lift generation, but you have a negative Cm naught being generated. So it does not trim the aircraft at positive angle of attack. So we introduce something known as a reflexed airfoil. What happens here is you have a slight curve towards the end. Right? So you have something like this. What happens here is that it produces a positive. So your effective lift generated here reduces. All the drag increases, lift generated reduces. So what happens here is when you transfer the forces, so center of pressure, I will move somewhere here. It will not move drastically with angle of attack in reflex airfoil, but if the center of pressure is here, and aerodynamic center is here, your lift and drag forces were initially here. When you transfer it to the aerodynamic center, you have a positive moment. So CMAC is greater than 0 for a reflexed airfoil. Okay? Does this make sense?
Okay, ma'am. Okay, ma'am. Understood now.
Any other questions anyone else has?
So, ma'am, we are considering CMAC for a camber dipole negative because it is we are having a net anti-clockwise moment about
Yes.
AC,
Yes. So
and for
the
reflex
convention
it
that
is
we-
positive since it is clockwise.
Yes. So the convention is
Okay.
have a pitch down. So this effectively it's pitched down, right? So that is,
Mhm.
and this is positive. Pitch up is
Positive. Pitch up is positive.
that is
So,
a
ma'am, by the term trim, we basically mean that the aircraft is in static equilibrium.
Yes,
No
yes.
additional forces or pitching moments are acting on it.
Exactly. It's in equilibrium. Correct. Static equilibrium. You're absolutely right.
All right, ma'am. Thank you.
You're welcome. Any other questions? Anyone else? Does anyone have any questions? Assignment 3 or this entire session? Any questions? Okay. If not, you can leave. We'll end the session here. We'll meet again next week, same time. Good luck for your assignment 4.
Thank you, ma'am.
Thank you.
Thank you, ma'am. Thank you very much.
Thank you, ma'am. Thank you very much.
Thank you, ma'am.